Every time you hit delete, your computer must warm the universe, literally. Not because it's sloppy engineering, but because physics charges a toll for forgetting. So where does a bit's information go when the machine forces it to vanish with no trace? Think about the simplest possible memory. One bit, not poetry. A physical thing that can be in one of two stable states. A little magnet that points left or right. A tiny capacitor that holds charge or doesn't. A flip-flop in a chip where one transistor is winning over the other. We like to talk about bits as if they're pure math. A zero floating in platonic heaven. But your computer doesn't store heaven. It stores a lump of matter arranged so that it can reliably be in state A or state B, and so that another lump of matter can check which one it is. So when you hit the delete key, what are you really doing? Your first instinct is nothing serious. You're just telling the machine, forget that file, and the machine obediently stops remembering it. End of story. But physics doesn't do forget for free, because forgetting is not the same operation as changing. If you take a bit that you know is 0, and you flip it to 1, you haven't destroyed information, you've transformed it. The process can in principle be done reversibly, meaning if I show you the final state, and I also keep track of what operation I did, I can run the movie backward and recover exactly what happened. Erasing is different. Erasing is the act of taking an unknown bit, could be 0, could be 1, and forcing it into a standard state like 0, while refusing to keep any record of what it used to be. That sounds innocent. It sounds like setting a variable to 0, but look at it in slow motion. Before erasure, there are two possible logical states the memory could be in. After erasure, there is only one. You've squeezed two possibilities into one outcome, and the moment you do that, something deep happens. You have made a many-to-one mapping, a logically irreversible step. There is no way from the final state alone to deduce the initial state. The past has been smashed into a single present. Now you could say, so what? That's just logic. But logic has to live inside the universe, and the universe has rules. In particular, it has a rule about what you're allowed to do when you try to compress possibilities without paying for it. Here's the puzzle in one sentence. How can you destroy information without leaving a physical trace? Because if the laws of physics at the microscopic level are reversible, atoms bouncing around according to equations that don't care which direction time points, then where exactly does the information go when you erase it? It can't just vanish. Not in a lawful universe. If the world were a perfect billiard table of atoms, and you knew every position and every velocity, then in principle you could run the whole thing backward and reconstruct the past. That's what reversible means. So if the microscopic laws don't allow forgetting, how can a macroscopic device, your laptop, perform forgetting millions of times per second? That's the problem. A computer seems to do a logically irreversible thing constantly, and the universe doesn't like irreversibility unless you pay. The payment is heat. Not as a metaphor, not kind of like heat. Actual energy dumped into the environment as random molecular motion, and the astonishing part is that there is a minimum price. Even with a perfect machine, even with perfect engineering, even if friction vanished and your wires were superconductors and your transistors were magical, there's still a floor, a thermodynamic toll booth. This is Landauer's principle. To irreversibly erase one bit of information at temperature T, you must dissipate at least K_BT ln 2 of energy as heat. And that number is not arbitrary. The ln 2 is screaming at you. Two states became one. Now that energy is tiny. At room temperature, it's about 3 × 10 circumflex, minus 21 joules per bit. Laughably small. You won't feel your laptop get warmer because you deleted one photo. But delete 1 trillion bits in a data center running day and night and you're suddenly not laughing. You're paying an electric bill. You're building cooling towers. You're fighting a very old enemy, entropy. So we need to make the question sharp, because otherwise it sounds like a cheap trick. Here's a sharper version. Why does the act of resetting memory, forcing a physical system into a known standard state, have an unavoidable heat cost, even in principle? Not why do real computers waste energy because of resistive wires and imperfect components? That's engineering. That's not interesting. The interesting claim is stronger. Even an ideal computer built by angels must warm the universe when it erases information. That is a weird claim. It sounds like you're mixing categories, like saying deleting a sentence makes the room hotter. So let's build a mental image that doesn't hide behind silicon. Imagine a 1-bit memory as a tiny particle in a box with a divider in the middle. If the particle is on the left side, call it 0. If it's on the right side, call it 1. Simple, physical, no mysticism. Now suppose you want to erase the bit, meaning regardless of whether the particle is left or right, You want it to end up on the left. You want to standardize the memory so the machine can reuse it. If the particle starts left, you do nothing. If it starts right, you must somehow push it to the left. But you're not allowed to peak and condition your behavior on what you see, because that peaking would itself require memory. You'd be storing information about the state, and then you just move the problem. You didn't erase information, you relocated it. Erasure means no matter what, the memory ends in a known state, and any record of what it was is gone. So in this box picture, you're trying to take a particle that might be in either half and compress it into one half without keeping any trace of where it was. That word compress is where thermodynamics walks into the room. Because when you compress a gas into half the volume, you can do it reversibly if you go slowly with a piston carefully balanced, and you can even get the energy back by expanding it again. But you can't compress without consequences if you insist on not knowing where the molecule was and not keeping track of anything. The missing information becomes entropy somewhere else. And entropy has a physical expression. It shows up as heat. So you start seeing the shape of the argument. Erasing a bit is like taking a system with two possible microstates and forcing it into a smaller set of possibilities. When you reduce the number of accessible states of the memory, you must increase the number of accessible states of the environment so that the total accounting works out. The universe doesn't care about your files, it cares about the total number of ways the microscopic stuff can be arranged. Information, in this sense, isn't a human invention, it's a measure of physical possibility. And this is where people get confused, because we're trained to think of information as meaning messages, secrets, knowledge, like something in a mine. But in physics, information is more brutal. It's how many distinct states could the system be in, given what you know. If you erase, you reduce what the system could be in. You reduce uncertainty about the memory. It becomes definitely zero. That reduction has to be paid for by increasing uncertainty somewhere else, usually the surroundings, usually in the form of microscopic agitation, heat. So the problem is not computers run hot. The problem is this. A computer is a machine that constantly takes structured distinctions, 0 versus 1, this file versus that file, this branch of a computation versus that one, and then at key moments throws distinctions away. It collapses alternatives into a single outcome. It cleans up, it resets, it forgets. And every time it does genuine forgetting, logical irreversibility, it has to dump entropy into the world. So the question we're going to chase is not whether this is true in some philosophical sense. The question is, can we see with our own reasoning why the minimum cost is exactly K_BTLN2? Why that shape? Why that scale? Why the universe demands a receipt every time you say, I don't need that bit anymore? Because once you see that, delete stops being a software command. It becomes a thermodynamic event. Because once you see that, delete stops being a software command. It becomes a thermodynamic event. So let's earn the number, not just the vibe. Why K_BTLN2? Why not K_BT? Why not whatever your laptop happens to waste? Go back to the 1-bit memory as a particle in a box. 2 halves. Left means 0. Right means 1. You want an eraser button that guarantees after you press it, the particle is on the left. Every time, even if you don't know where it started. Now, if you were allowed to know the starting side, you could do something clever. If it's already left, do nothing. If it's right, gently push it left and maybe even recover energy on the way. But that allowed to know is the trap, because knowing is itself information. If you store it was right anywhere, you've just moved the bit, you haven't eliminated it. Erasing means no record survives, not in the memory, not in your controller, not in some little notebook attached to the piston, nowhere. So the eraser has to be a blind procedure, same physical protocol, regardless of whether the particle is left or right. Here's a protocol that works and makes the physics obvious. 1. Remove the divider. Now the particle can be anywhere in the full box. Left or right doesn't exist anymore as a meaningful distinction. 2. Slowly insert a piston from the right side and compress the volume until only the left half remains accessible. Now the particle is guaranteed to end up in the left half. 3. Reinsert the divider. Done. Bit reset to 0. That's erasure. And you can feel where the cost is hiding, the compression step. Because if the particle is free to roam the whole box, then forcing it into half the box is literally a gas compression problem, even if it's one molecule, even if it's 1 bit. And in thermodynamics, compressing a gas slowly at temperature requires work. If you do it reversibly and isothermally, the work is W equals sign K_BT len, left of V initial volume is the full box, the final volume is half, V2, so while W equals sign K_BT len 2, there's your number. Not because information is magic, because erasing a bit is, at the level of physical possibility, identical to compressing the accessible phase space by a factor of 2. Two logical states become one. Volume becomes half. Same mathematics. Now where does that work go? If you do the compression perfectly slowly, in contact with a thermal bath at temperature T, the particle pushes back. You do work on it, but because you're keeping the temperature constant, the extra energy can't stay as organized energy inside the one molecule gas. It leaks out as heat into the surroundings. So the best case erasure, the ideal reversible compression protocol, turns the work you supply into heat dumped into the environment. Exactly, K_BT len 2 per erased bit. This is why Landauer's statement is so clean. It's not computing cost energy, it's throwing away distinctions cost entropy. The entropy change of the memory is delta S memory equals sign minus K_B len 2. You've reduced the number of accessible states by 2. Entropy went down. The second law is basically the universe saying fine, but if entropy goes down here, it must go up somewhere else by at least the same amount. So the environment must gain delta S memory K_B len 2. And at temperature T, an entropy increase, delta S corresponds to heat Q dumped. QGET delta S equals sign K_BT len 2. Same result, different angle. So the heat of forgetting isn't a quirk of computers. It's the cost of making the past unrecoverable. Now you might object, wait, that protocol started by removing the divider. Isn't that basically scrambling the bit first? Aren't you cheating? No, that scrambling is exactly what erasure means. When you erase, you destroy the correlation between what it used to be and what it is now. Removing the divider is the physical representation of destroying that correlation. You are deliberately making the two states merge into one physical description, particles somewhere in the box. Then you force the merged description into a standard region. That's what makes the mapping many-to-one. That's what makes it irreversible. And if you try to avoid the many-to-one step, you discover something very important. You can compute without paying this cost if you never erase. This is where people get their minds twisted, because you've heard somewhere that computation must dissipate heat. Yet here we're saying something narrower. Only logically irreversible operations require a minimum heat cost. So what about all the other operations? And Oregon not, are those inherently irreversible? A typical AND gate is logically irreversible. If I tell you the output is 0, you don't know whether the inputs were 0, 0, 0, 1 or 10. 3 different pasts collapse to one present. That's many-to-one. That's information loss. But you can build reversible logic gates like the Toffoli gate that map inputs to outputs 1-to-1. If you know the output, you can reconstruct the input uniquely. No information is destroyed. In principle, a reversible computer could perform a computation with arbitrarily little energy dissipation by doing everything slowly and carefully, like an ideal piston. So why don't we do that? Because reversible computation has a catch that's almost comical. It refuses to forget, ever. To keep the mapping 1-to-1, it has to keep all the intermediate junk information that ordinary computing would happily throw away. The machine accumulates garbage bits, records of the path taken, because erasing them would be the very act that costs heat. So you can postpone the payment, but you can't cancel it. If you want a finite machine to run forever, eventually you need to reuse memory. Reusing memory means resetting it. Resetting means erasing, and that means paying Landauer. This is the universe's bookkeeping style. You can't have a perpetual computation without either infinite memory or heat production. Now if you're thinking about Maxwell's demon, the little creature that sorts fast molecules from slow ones to extract work from thermal noise, good, because Landauer is the modern resolution of that headache. The demon seems to get free work by using information. It measures molecules, opens a door at the right time, and creates a temperature difference. Free energy from knowledge. Sounds like a cheat code against the second law. But where does the second law sneak back in? In the demon's memory. The demon has to store measurement results. Fast on left, slow on right, yes, no, open, close. That's information. If the demon is to operate cyclically, it must eventually clear its memory to make room for new measurements. That clearing is erasure. And Landauer says every bit the demon erases costs at least K_BT len 2 of heat dumped into the environment. So the demon can extract work, yes, but only by paying the same amount back when it wipes its slate clean. No free lunch, just accounting. And notice something subtle. Measurement itself doesn't have to cost K_BT len 2. In principle, measurement can be done reversibly. You can correlate a memory with the system without immediately throwing anything away. The cost comes when you insist on returning your measuring device to a standard ready state, when you demand amnesia. That's erasure again. So the Landauer limit is not a moral lesson about arrogance. It's a technical statement about cycles. A memory that participates in a cycle must be reset. Resetting is physical compression of possibilities. Compression costs work. Work turns into heat. Now bring it back from demons and boxes to the stuff on your desk. A bit in a real computer is not literally a particle in a box. It's often a voltage level. Two basins in an energy landscape. A low state and a high state separated by a barrier so thermal noise doesn't flip it constantly. Erasing that bit means forcing the system into one basin regardless of where it started. The usual way is to apply a voltage that tilts the landscape so the zero basin becomes the only stable one. The state relaxes. Energy is released as heat in the lattice vibrations of the chip. The atoms jiggle. Phonons heat. Could we do it closer to the limit? Yes, by doing it slowly and carefully so we don't create extra dissipation. People have actually measured near Landauer erasure in small systems, nanomagnets, colloidal particles, and optical traps. It's not just theory, but the limit depends on temperature. Lower heat, lower cost. So you might get an idea. Fine, I'll erase at very low temperature. I'll make the cost arbitrarily small. You can push it down, but you can't escape the structure of the rule. The cost is proportional to T, because thermal randomness is the currency of entropy. And to operate at low temperature, you need refrigeration, which itself costs work and dumps heat somewhere else. Again, accounting. And there's another practical catch. If your bit is sitting in a thermal bath at temperature T, and you want it to be reliable, the energy barrier between 0 and 1 must be high compared to K_BT. Lower temperature helps reliability, but the third law of thermodynamics tells you that reaching absolute zero takes infinite steps. You can't get to zero cost by simply wishing for T=0. So the upshot is brutal and clean. Information is physical because a bit is a physical degree of freedom with alternative possible states. Erasing is physical because it is the act of collapsing alternatives without keeping the missing distinction anywhere. And collapsing alternatives, making the past unrecoverable, forces the universe to create entropy somewhere else, which is just a polite way of saying you heat the world when you forget, which is just a polite way of saying you heat the world when you forget. Now, if you're honest, that sentence should bother you a little, because you don't just erase bits on a computer, you erase them in your head. Every time you decide that detail doesn't matter and you let it drop. Every time your brain overwrites a short-term impression with the next one. Every time you learn a new phone number and the old one vanishes. You are not a ghost watching the universe. You are a physical system inside it. And if information is physical, then cognition is not some airy, frictionless act. It's chemistry doing bookkeeping. So let's zoom out and make the logic tight. Landauer's principle is not saying energy is needed to store information. You can store a bit in many ways, and the energy differences can be tiny. You can even in principle move information around reversibly with arbitrarily little dissipation. It's saying something more specific and more frightening. The moment you demand irreversibility, when you demand that a previous distinction be truly destroyed, you must export entropy to the environment. And exporting entropy in a warm world means heat. That's why the delete key is not innocent. It's a command to take structured, recoverable correlations and deliberately smash them into a standard state. And the universe doesn't let you do that silently. It makes a sound, not an audible sound, an entropic one. Random molecular motion in the air, in the silicon lattice, in the coolant, somewhere. Now here's the part that people often miss. The heat doesn't come from the bit, like it's a little glowing coal. The heat is the price of making the operation irreversible while staying compatible with reversible microscopic laws, because the microscopic laws don't erase. They move information around in the correlations between parts. So when you erase, what you're really doing is forcing the missing information to become inaccessible, dispersed into degrees of freedom you are not tracking. The environment, the thermal bath, the countless microscopic states of the world, that dispersion is what we call entropy increase. So the word forget becomes a physical verb. To forget is to spread information into places where it is practically unrecoverable. And practically unrecoverable is not just psychology. It's statistics. It's combinatorics. It's the sheer ridiculous number of ways the molecules in a room can jiggle. Once the information is smeared into that ocean, you're not getting it back, not because the laws forbid it, but because you'd need absurd control over an absurd number of microscopic details. You'd need to reverse the universe's dice roll. That's the real meaning of irreversibility. Now you might want to push back with a comforting idea. Okay, fine, but the Landauer cost is tiny, so who cares? Good, let's respect the numbers. At room temperature, K_BT Len2 is about 3 times 10 circumflex minus 21 joules. If you erased a billion bits, about 125 megabytes at the absolute theoretical minimum, you'd dissipate roughly 3 times 10 circumflex minus 12 joules. That's nothing. A speck. So for your laptop today, Landauer is not the main reason it gets hot. Real machines waste vastly more due to resistance, leakage currents, capacitance charging, imperfect switching, and all the messy stuff engineers fight. But dismissing Landauer because it's tiny is like dismissing the existence of atoms because you can't see them. The point isn't that this limit dominates your electricity bill right now. The point is that it exists at all. That the universe has a minimum price tag for the act of erasing a distinction. That information is not just a story humans tell, it's welded into thermodynamics. And once you accept that, you start seeing computation differently. Your phone is not a pure logical device that happens to be implemented in matter. It is matter doing logic. It is a machine that rearranges physical degrees of freedom into patterns that stand for decisions. And every time it tidies up after itself, every time it clears a register, frees memory, drops a bit, it has to dump entropy to stay honest. Now take one more step outward. A living brain is also a computer in this sense, not because it runs Python, but because it takes in signals, stores correlations, updates states, and discards information all the time. Your neurons burn glucose, they move ions, they pump sodium and potassium across membranes to maintain gradients. Gradients are low entropy structures. They're like little charged up batteries, and when a neuron fires, it partially spends that structure, it makes a pulse, then it has to restore the gradients. That restoration costs energy and produces heat. That's why your brain is warm. Not metaphorically warm, literally. You are running a 20-watt organ in a bag of water, and you have to dump that heat into the world, through blood flow, through skin, through breath. Thinking is a thermodynamic event. Now, I'm not claiming you can calculate one thought equals X joules. Brains are not neat digital machines. They don't erase bits and clean registers the way a toy model does. But the principle doesn't care about implementation. If the process includes any logically irreversible step, any deliberate discarding of information to reset, simplify, compress, decide, then the second law is sitting there with its ledger. No exceptions, not for biology, not for consciousness, not for beauty. This is the existential punchline hiding inside a dry equation. You cannot have a mind that updates itself without paying entropy, because a mind is in part a memory manager, and memory management at the deepest level is thermodynamics. When you let go of a detail, the universe doesn't just nod politely, it accepts the detail as heat. So what does this mean in a larger sense? It means that the boundary between information and physical reality is fake. A useful fake for daily life, but fake. A message is not floating, it's ink molecules on paper, voltage levels in silicon, spin orientations in a magnet, protein states in a synapse, always something. And the act of making knowledge usable, storing it, copying it, processing it, always comes with a physical trail. Sometimes the trail is reversible and can be made almost free. But the moment you insist on finality, on wiping the slate clean, finality costs heat. That's why the arrow of time sneaks into your laptop. Your processor doesn't just compute. It creates a little arrow of time every time it resets a bit, a one-way step that increases the entropy of the world and makes the past less accessible. That's an odd thought. Your machine is manufacturing irreversibility. Bit by doing the one thing the microscopic laws refuse to do on their own, throw information away. And you do it too. Every day you compress your life into a manageable story by discarding almost everything. Your sensory system is flooded with data. Your conscious mind keeps a thin summary. That summary is you. And the discarding is not nothing. It's physical. So the next time you hit delete, pause for half a second. Not to be dramatic, to be accurate. You are not removing a ghostly idea. You are forcing matter into a standard state and paying the universe an entropy. A small payment, but fundamental. If you want more of this physics where the equations point back at you, where reality includes your own thinking, stick around, because once you stop treating information as abstract, you start noticing that the universe is not just made of stuff, it's made of constraints, of what can be distinguished, of what can be remembered, and of what it costs to forget.